Welcome to my solution of Advent of Code 2022, Day 7 in C++. So the task today is to parse a console output of traversing a directory tree. So we have change directory commands and listing commands. And from parsing this console output, we shall build a tree and calculate how large each directory is, because we only get the sizes for the files inside these directories. And as a final touch, we're going to select the directories, not select any files, select directories that are at most 100,000 bytes in size. So that's the task for part 1. So here's how I did it. First, I parse the input into a data model. Then I create a directory tree with this data model. I print the directory tree. I have some old code here, you can disregard that line. Then I call this recursive depth first search, providing the tree and the root path. As a result of that, I get a mapping between path and size, which will include files. So what I do inside here is that I have a logging, and then I check if the path I'm examining has subdirectories, that is, adjacent vertices. If it has, and the size mapped to that path is less or is at most 100,000, then I accumulate the size of that into result, and I have a logging out there, and I return the result. So now we have 2 parts to look at, or actually 3 parts. The parsing function, the tree object, and the depth first search. So the parsing is straightforward. I read lines, then I use a new iString stream of that line and use that to separate this line into tokens. So I accumulate the tokens and then I push the tokens back on result. So result will be an entry with a vector of tokens for each line in the console input. The constructor of this directory tree takes this data model and turns it into a directed tree. So this tree is implemented as using an adjacency list and a mapping between path and size. So parsing, I just used brute force. The first token can be either a $sign or it could be the text dir, else I just assume it's a file entry. And the walking of the tree happens in the command part here. So if the command is change directory, we check if we're going up. If we're not going up, we're going down. So I have this current directory helper variable here, and if I'm going up, I just pop the last entry from the path, otherwise I push to the path. The listing command I just ignore, I don't have to do anything with it. For a directory entry, I add an edge to the tree from the current directory to the vertex, either the file name or directory name, with a size of -1. This was unnecessary, but that was how I wrote the code. So just ignore the -1 there. The file entry, then I just turn token 0, which is the file size, and I add an edge with that size. So easy enough. We have some helper functions here, we can ignore that. The add edge, just look at it, it's straightforward. It takes a path from, it takes a vertex and a size, and it updates the adjacency list from with this vertex. And please note, from is the whole path, and vertex is just the file name. And then I have a guard here, so I only update sizes that in effect are for files. So if size is greater than 0, then I update the size mapping here with size, and we have some logging. That should cover the tree implementation. Ignore this class, it was just an experiment. But here we have the function recursive depth first search. And the way I implemented it is that it takes a tree and a source where to start. And this is recursive. So when we get a path, what we do is we check if this path, if it has no adjacent vertices, that is, it's a file, it doesn't have any subdirectories. In that case, I map this source path to the size of the source. And this size is known because it's a file. Otherwise, I accumulate the size from subnodes. So I loop through the adjacent vertices, that is subdirectories, and I calculate the subpath as the input path, i.e. the current path, and I push back the connected vertex. So now subpath is the path to a subdirectory. I do a recursive call. So X here is just I didn't have enough fantasy to name it. So X is now the result of recursing down to the subdirectory. So when we come up here, we have mapped all the subdirectories to sizes bottom up. And now what I have to do is I have to loop through these entries in X and insert them, update my result on this level, and also accumulate all the sizes in the subdirectories from source, and then I just update source with this size. So it's a bottom-up accumulation of the sizes. Some logging, and then we return the result. So I think, if I haven't forgotten anything, I now explain part 1. And for part 2, the only thing that differs is that now we are interested in identifying a directory to delete to free up space so that we get 30 million bytes free. And we know that we have a total size on the device of 70 million bytes. And also we are going to find the smallest one we can delete to get free at least 30 megabytes. No, sorry, 30 million bytes free. So for part 2, the first part is exactly as part 1. I create this mapping between path and size. I look up the size of the root directory in this mapping. I calculate the free space, which is the total space minus the root size, what the root size occupies. Some logging, and then I calculate what to recover. And what to recover is I need 30 million bytes, and I have this amount of free space. So what's missing? I instantiate a candidate list, which is this mapping between path and size. And then I copy only those that are directories and have a size that is enough to get this size to recover. So the copy-if function here, it takes a, sorry about the code completion irritation here. I use a standard inserter into candidates, and I call it with a lambda, that takes the tree and the size to recover, capture that, and it checks the entry if the entry has adjacent nodes. That is, it's a directory, it has subdirectories and files. If it passes that and the size of that entry second, the mapping, is greater or equal the size to recover. So now we have all the candidates here, and the only thing left to do is to find the smallest one of these candidates, and it's just to call mean element looping over the candidates with the lambda checking the size, which is entry second in the mapping here. And the final precaution, I check that the answer I got is actually valid and not that it found it, and if so, I set result to the mapping, which is the second there, the mapping size. So there you have it. Took me some time to get all the bits and pieces in place, but once it's ready, it's easy enough. So if you have, thank you for watching and see you tomorrow. Okay, good morning, Internet. 2 minutes late this morning, 0600 here in Sweden, Stockholm. Let's see. Now I think I got it correctly, so I'm going to let it loose on the actual data. Okay, that doesn't work. Back again, so now I refactored the tree, the file directory tree, so that each vertex is mapped to a path. Fingers crossed. Oh, okay. Well, better late than sorry. Let's continue to part 2. Some coffee and some rest, and now we can go to part 2. Fingers crossed, we'll let this loose on the final problem. Looks a little small, doesn't it? Ah, okay. So once I got the recursion straightened out and used the path instead of the vertex, this was not that hard. So anywho, maybe I clean this up, but for now, thank you for watching and see you tomorrow.
If you like my videos, feel free to do nothing. Just grab a cup of coffee
and enjoy.